Is it recording? I think. I hope so. All right. So
your video is not up, though.
Sorry?
The video of you is not up. I don't know if you're interested in having that since you were on video before.
Oh, yeah, I can see myself. Can people not see me?
No.
No.
Oh.
The recording's off.
But it does say that the recording has started, so that's good.
That's good.
That's good. Okay, that's good. Yeah. All right, that's good. So I guess we're being recorded now. So I can just see myself. I don't know why you can't see me. All right.
Oh, we're good now.
Oh, okay, good. All right. Well, I turned it off and back on the camera, so I guess that worked. All right, great. So sorry about that. So hopefully the recording will, will work, and I will then post it, I guess, on the YouTube channel. Right. So welcome to this class, I guess, CS867 and QIC890. Maybe one thing we should do is to just kind of say hi, and maybe if everybody can briefly introduce themselves so that we don't feel lonely in the online portion of the class. So I'm Shalev. I'm assistant professor here. I guess it's my third year now at Waterloo. And I guess I'm physically in Waterloo. I'm not sure where everybody else is, so I guess maybe you could also tell us briefly where you are. Maybe a little bit of what you're studying or what you hope to get out of the course, if you want to say that. Okay, who wants to? Should we go by the list? We can go by the alphabetical list of people. There's a list of participants. Hopefully you can see that.
Hi everyone. I'm Abhishek. I'm a master's student at Waterloo under Professor Shalev. I'm currently in India, right, for this semester at least. And I guess I just want to learn more about query and communication complexity.
Okay. I guess Andrew.
Hey guys, I'm Andrew Jenna. I'm doing a PhD with Mikola Mosca, and right now I've been doing a lot of quantum chemistry, but I've also dabbled in quite a bit of crypto, and I really like quantum complexity theory, and it sounded like a fun course.
All right. Danny?
Hi, I'm Danny Kong. I'm a student of Richard Cleave, and I'm also interested in studying like quantum complexity. And I'm a master's student as well.
Okay. All right. I guess if everybody's only going to say that they're interested in the course or whatever, then it's okay to skip that part. So I didn't mean to make everybody repeat that. So thanks though. Yeah, that's fine. I don't mean to embarrass anyone. But all right. Jin Tiao.
Hi. So my name is Randy. I'm a first-year master's student under Richard Cleave. So I'm there's a pretty good chance I'm sitting in this course because I took another course with Shalev 2 terms ago, and this covers a bit of newer material, which is mainly the communication complexity, which I'm interested in. I guess since we are saying more, I'm interested in the MIP star equals RE result. That's my
We probably won't cover that.
But no,
yeah,
for sure. I don't think anyone knows what's going on with that paper yet.
Yeah. So the course you took in the summer should have maybe around 50% overlap with this course. So
it's nice to see.
I don't know. I don't know if you're like auditing or officially taking it, but there will be some overlap. So I don't know.
Still deciding.
Yeah.
But it's nice so that there's more people in the chat now.
Yeah. Okay. Lane?
Yep. So I'm Lane. I've been in Waterloo since 2017, finishing my master's and doing my PhD now with David Corey. I mostly work in high dimensional quantum error correction codes, theory related to that, and some stuff related to mesoscopic physics. And I'm taking this course because I like this subsection in quantum algorithms.
All right, and I guess, Lane, I owe you an email. You emailed me and I never responded.
Oh.
Sorry about that.
Yep, just when you get a chance.
Yeah, I mean, you sent me like this attachment and I meant to read it, and you know, because of that, then I never responded because I kept meaning to look at it more thoroughly. So, yeah, I'll hopefully I'll get to you. You feel free to send me a reminder if I keep ignoring you for another few days. So just send me another email. Don't feel bad. Yeah.
Okay, will do.
Yeah. Okay, Natalie.
Hi, I'm Natalie. I'm starting this term my master's with David Gossett, and I'm interested in quantum algorithms and want to learn more about complexity theory and query complexity specifically.
All right. Olivier.
Yep, close enough.
Your name? Sorry.
Can you guys hear me?
Yep.
Great.
Can you say your name again, though? Yeah.
Yeah, it's Olivier.
Olivier. Okay.
Or Olivier, if you want to be all French about it. So I'm a first year master's student under Olga Vechimova. I'm working in the NLP lab, and honestly, I'm not sure. I kind of I was baited by the really cool keywords in the class title. So that's really why I'm here. So we'll see if what I can get out of it. But it looks really fun.
All right. Cool. Yeah, sounds good. Tony.
Yeah, hi, I'm Tony. So I'm another master's student under Richard Cleave, and so I'm kind of studying non-local games and interactive proofs and stuff, but complexity theory in general is pretty interesting, so that's why I'm interested in this course.
All right. Cool. And Yu Ming.
Okay. Hi, everyone. I'm Yu Ming. I'm a first-year PhD student working with William Slofstra. So my research involves a lot of C-side algebra stuff. So complexity stuff is pretty new to me.
Okay. And Zhuang Fei.
Yeah, Zhuang Fei. So hi everyone. I'm Zhuang Fei Hu, and I'm my main research direction is software engineering, and I'm under the SWAG lab. My supervisor is Mike Software. So my main research topic is like rather irrelevant to this course, but I'm very interested in this topic. And I took CS867 during my undergraduate period. Yeah, and I just have some very basic idea of this like quantum complexities and theories. But I'm really interested in it, and I hope to learn more about it in this course. Yeah.
All right, great. So, okay, and it looks like we have here, if I'm reading it right, 10 students plus me in this meeting, I guess. So the official registration is 15. I'm not sure for the other 5 if they just couldn't make it or if they're like planning to drop. So we will have to see, but I will definitely post this recording and hopefully we can see some engagement from them as well. All right, so yeah, so thanks everyone. So did people get a chance to look at the notes or the video that I posted? I apologize again. The video is kind of, not the highest quality. I will try to improve it, making it. So does anybody have any kind of feedback on that or any questions?
There were, I think, 1 or 2 minor typos. Do you want me to note them, or I mean,
well,
in an email, would you like them noted, or?
yeah, either in Piazza if you want others to see it, which is fine, or in an email. Piazza's okay. I mean, I don't, there's no problem to have others see it, or private note as well on Piazza if you don't want, if you're afraid of that it's wrong or something, don't want to embarrass yourself, then private note is fine.
No, this is more like accidental symbol typing.
Oh yeah. So then, yeah. So why don't you just put it on Piazza? I think that's easiest for me. Then all the class-related content is in one place. My email's a bit messy, so it's a little easier for me if you put it on Piazza. And then, yeah, don't tell me now because I won't. I'll have to
I don't have them offhand anyway,
yeah.
so it's good.
Yeah. Yeah. Thanks. Did anybody watch the video? I know it's kind of end up being a long video. It's okay if you prefer to read the notes in general. Just wanted to give people an option. Actually, so I don't know if people are too shy to answer the question or if they did not watch. Why don't you you can at least type in the chat. So how about if you watched more than like 15 minutes of the video, say so in the chat. Oh, okay.
Oh, yeah, raising hand, I think.
Raising hand, oh, yeah, that works too, yeah. Okay, 3 people now, all right, 4, 5, okay. So a bunch of people did watch it. Oh, okay. So in that case, a lot of people watched more than 15
almost
minutes.
everyone.
All right. So, yeah. Yeah, so roughly half the people. That's pretty good. So any feedback on that? Just any advice you have? I assume people have attended more online courses than I have. I don't know if other people have better solutions to, say, the online whiteboard, which I don't think I was using optimally. And just if you could hear me, I don't know if there could have even been lag in the recording. So I don't know if any technical feedback or content feedback.
Well, my main concern was that there were a couple places where audio cut out in the video.
Oh, the audio completely cut out?
Yeah.
I see.
It was kind of hard to tell what was going on.
Yeah, there was I had a problem that I was trying to record on the computer, but use the whiteboard app on the tablet. And yeah, and the audio was actually coming from the tablet, which I later realized is not optimal because they're only connected over the Wi-Fi. The tablet, was not plugged through a wire, so it was only through the Wi-Fi, and I didn't expect it to completely cut out. Actually, I tried to briefly check, but I didn't listen to the whole thing. Yeah, so I thought it might be laggy at points because of that, but completely cutting out is a problem. All right, was it the large sections or?
It was mostly like a couple small sections.
Okay. All right. Interesting. So yeah, I'll have to come up with a better system for doing this. Yeah, I'm gonna I need the tablet to write on. So yeah.
Are you using like a tablet like an iPad or like a drawing tablet?
It's just an iPad. I don't know. Is there an advantage to buying a dedicated drawing tablet for this?
Randy, do you have thoughts on this? Because you have one.
I just think it's the reason why I got a drawing tablet is because I don't have to buy an iPad.
Okay.
But
I mean, I
think
tried to look for the difference online. Nobody seemed to be able to tell me what the difference actually is. So
this
I didn't
is
know if
a 30. This is a $30 drawing tablet, and it works pretty well, both for office hours and just group meetings in general.
Okay.
And
do you use it? Like, do you have when you use it? Is it like, do you plug it in and use an app, or you just how do you
just
do it?
plug it in and draw it on OneNote, for example.
Okay.
And you can kind of use the screen sharing function in Teams.
I see. Yeah. So maybe I should. Yeah. Well, okay. Next time I'll try to plug the device and use some app. So what I did, maybe you don't need to be bored with the technical details. But what I did was I
I'm
just
interested to
joined
hear them. Yeah.
Yeah, I just joined the call through the tablet and through the computer as well. So then you know, because I joined the call, I was able to kind of share a screen from the tablet. And so that's how I was. So I didn't. Yeah. So then the tablet was sort of on the call through Wi-Fi, and that seemed to at times, you know, have connection issues. All right, fine. I will try to improve for next time. So I don't know if so. Did people do people prefer kind of more video or more written notes in general? Or I don't think I'll be able to do both for every week.
How should we vote for this?
Yeah, that's a good question. Let's say So let's say maybe people can one person still raising their hands, but I mean in general, if people can raise their hands for if they prefer the notes to the video, maybe people can raise hands now. Okay.
Wait, you're saying prefer notes over video or video over notes?
The notes, prefer notes. Yeah. All right. Okay, and okay, so I guess I see like 6 to 7-ish. All right, so what about people who prefer video? So if you prefer video, raise your hand. Just to see. Okay, so most people prefer notes, but there are a couple people who prefer video. Okay. All right, that's fine. So I'll see if I can occasionally put out videos as well. Right. So for this week, so I was thinking of putting some notes for just some basic quantum algorithms. So basically, well, pretty much just Grover search and some, you know, Shor's algorithm or quantum Fourier transform, and how they work in query complexity, in case people have mostly seen them kind of not in query complexity. Just to get kind of used to the notation a little bit. So I think I will post some notes on that, I guess. Not sure if I'll have time to make a video as well. And then, so I wanted to post readings as well. So for readings, I was thinking of posting. There's kind of two papers that did what's called quantum amplitude estimation. So have people seen this algorithm before for quantum amplitude estimation? It's kind of similar to amplitude amplification, but it's not quite the same. Okay. Yes. Okay. So I'll mention a little bit about it in the notes, though, right? And then there's one kind of pretty old paper that did this, maybe back in '98 or early 2000s, so around 20 years ago. Yeah. So that's one classic paper that it did a long time ago. And then there's a recent kind of very simple paper that redid it last year, or maybe 2019, so maybe 2 years ago. And so so that one is particularly kind of nice to read because it simplifies the construction. So I thought that at least, so I kind of wanted to post both so that the students can compare the two. But the more recent one is the better one to read in detail because it's simpler. So there's kind of no reason to go to the older and more complicated version, except maybe to compare with the recent one. So I was, yeah, I was wondering if anybody wants to kind of volunteer to take up this more recent paper, and we will do a student presentation next time we meet. So probably early next week, on Monday or so next week. I don't know if well, if people don't want to volunteer now, I will ask on Piazza as well. So you can also briefly look at it first. And the advantage of Piazza is that some people might not be joining this video right now. So we technically have 5 students in the class who are not in the call. So I don't want to only ask for volunteers over video in general, in the general case, because it will miss people who don't join the video meeting. So yeah, but just for the first class, if anybody does want to volunteer right now, that would be totally fine. Okay. If not, all right, that's fine. So I will post it. We will need a volunteer to present a paper. Maybe in the next day or two. So I'll post it soon tonight, and then we will need somebody to take it up for Monday. And we're talking about like a short presentation. You don't need to read the whole paper from start to finish. You just kind of need to lead the discussion about it. So, roughly say what the content of the paper is. What are the main results? You can try to read through proofs a little bit. You don't need to feel so. Yeah, I mean, look, maybe this paper. I don't remember how long it is if it's trying to do other things, but maybe this paper is on the easy side. In general, I will post papers. Some of them will be pretty hard, and I don't mean for students to kind of work really hard to figure out everything that's in the paper. That's a lot of work. So when I post a paper and tell students to present it, I don't generally mean that you have to know everything in the paper. Papers, especially papers in kind of theoretical computer science, they've kind of grown in length recently. So I mean, they're now these 30 to 50-page beasts in general, especially the important ones. And it's a big chore to kind of read through them properly. So that's not what I mean when I say to present a paper. I just mean to kind of effectively present the intro of the paper, more or less. And that's also what I mean for you guys to read when I post a paper. But, especially if the introduction is easy to understand, if you can naturally keep on going, then you can try to read some of the key proof ideas as well. So I hope that this is not. I hope students are often scared of papers, to present the papers, especially if you haven't done it before. So I'm just trying to make this less scary. I don't mean to kind of have you be experts on everything in the paper, and it's definitely okay to not understand parts of it. Okay, so having said that, I guess we will. I'll post it on Piazza, and we'll wait for volunteers after. Just to tempt you a little bit, I do think this paper will end up being slightly simpler than the ones in future weeks. And I think we'll try to do only one presentation this week, so I'll post the older paper as well, but maybe there's no point to present it if it's kind of like a strictly more complicated version. So we'll only do one student presentation this time, but in future weeks, I expect we might do 2 presentations a week. So in general, I would hope that every student presents 2 papers in the class. And towards the end, we will be busy with project presentations. We won't have too much time to take up papers in the last week or so. So we don't have too many weeks of papers. We'll have maybe 10 weeks. If everybody presents twice, we're basically going to need 2 papers a week, roughly. Yeah, maybe even 3 if we really end up with 15 students who stay in the class. Yeah, so we might need 3 some weeks. Yeah, so some weeks I will also post more papers that I don't intend for students to present. So not every paper will be presented. Did anybody actually have a look at the optional readings? So I posted optional readings. I guess I did not expect people to really look at it. Maybe raise your hand if you did look at the optional readings. Okay, nobody did. All right, that's okay. It was labeled optional. All right. Okay, so right. So I will post the papers after we end the call. And then I will post the notes for this week a bit later, probably tomorrow. and then yeah, so I wanted to talk a little bit about the content. So you guys gave me some feedback on kind of the video and the writing, but how did you find the content? You know, was it was it too much content, or enough content? Did you already know it?
It was a pretty concise overview of the different query complexities, so it was a good review.
Okay. Thanks. Anybody want to disagree and give negative feedback? That's totally okay. All right, nobody's daring to do that. That's okay. I think you're able to leave anonymous comments on Piazza, by the way, if you want to kind of tell me that it was too long and difficult or something. Yeah. So right. Yeah. So maybe let's just briefly review the actual content, so that while we're all here. So I mean, in the video, I mostly only got through the definitions of the various query measures. In the notes go a little bit further, and they go through some relationships between query measures, and they prove some basic relationships between them for total functions. So just to review, so in both the video and the notes, we defined kind of deterministic query algorithms, randomized query algorithms, and quantum query algorithms. And the deterministic query algorithms ended up just being decision trees. So it's a kind of very simple mathematical object. You don't have to, it's not as complicated as Turing machines or something like that, the way you define algorithms formally in a different course. Randomized algorithms ended up just being probability distributions over deterministic algorithms. So that's also kind of mathematically a very simple object. And then quantum algorithms were not like that. So they were not just, say, some superposition over decision trees. They don't look like that. There's the relationship between randomized to deterministic algorithms is just one of adding a probability distribution on top, right? So you just add randomness sort of on top of the deterministic. But the relationship between quantum and these measures is not like that. You don't just add quantum on top. You have to kind of redefine everything from scratch. So both the notes and the video kind of go through that. And the intuition is sort of that we want to allow the algorithm to make queries in superposition. This might happen in practice. For example, if the input, I always think about it, imagine the input is given to you as kind of a USB stick. And the USB stick is computing some function, or it contains some database, for example, or maybe it's computing some function. But basically, when you pass it an input I, it gives you xi. So it gives you, you can always view the string x as itself basically a function. You give it I, and it returns xi. So the USB stick is performing this action, and you don't really know how. But what you can potentially do technologically is you can kind of make queries in superposition to this USB stick, which in practice would involve, cooling it down to near absolute zero, and I don't know what, doing some physics with it. I'm not very good at the quantum physics, so part of things. So but presumably it would involve cooling this thing to around absolute zero, and and then trying to pass in queries in superposition, getting responses in superposition. And the question is, does it allow you to answer questions about what this USB stick contains more quickly? So it allows you to ask a different type of question. So what type of things can you learn like this? And as usual, our only budget is the number of questions you ask the USB stick. So if it contains, if it's a database of length n on there, then after n questions, you know everything. So the query complexity is always at most n. But sometimes it's going to be much smaller. So often we think of n as actually exponential. We think of n as really big, and then so often we actually want to achieve polylog n. We want it to be polynomial in log n. That would often be a concept of like an efficient algorithm. Yeah, that's generally the query setting. And I guess what's remarkable about it is, I guess, as we'll see this week, most of the famous quantum algorithms actually naturally work in this model. So they actually, even though factoring doesn't sound like it involves querying a database in any way, actually secretly the algorithm is basically doing that. The algorithm, Shor's algorithm, basically is querying a database in superposition. In an intermediate, in the key part of it, the key part of the algorithm effectively does this. So even though the model sounds pretty limited, somehow it ends up capturing a lot of what quantum computing seems to be as we understand it. So as we understand quantum computing currently, a lot of the quantum speedups really come from being able to query in superposition and therefore not read the whole input, in a sense, like quote unquote. Of course, if you want to factor a number, you will read all the number. You will read the entire number, but then you will sort of implicitly turn the number into an exponentially long database of other numbers modulo this number, and then you will try to query that implicit database you're implicitly creating. You'll query that in superposition, and that's where Shor's algorithm gets its speed up. So yeah, I mean, I guess I'm just trying to sell this concept that it sounds artificial at first, but it ends up capturing a lot of where quantum speedups come from at the very least. It's also a reasonably interesting model for randomized algorithms. Practical randomized algorithms don't always look like query algorithms, but when you study the relationship, like when randomized algorithms give advantage over deterministic ones, this model becomes somewhat useful. Many of the lessons you can get from this model do generalize to other models as well. So it's kind of often people's first step. When you want to study some fundamental question, first you do it in query complexity. It's the easiest model, and then you go further. You can try to see to what extent this generalizes elsewhere to kind of computational complexity more generally. Yeah, and then so of course a key concept in query complexity is the difference between total and partial functions. So I mentioned it, I guess, both in the notes and video, but that in the so if we insist that the function has to be defined on every single input, it actually limits it limits us in what functions we can define in query complexity. It's kind of sort of in many natural settings, we actually already know something about the USB stick we got, or we already know something about the input X. We know it's one of these. Maybe we know it's one of these n inputs out of 2 to the n strings of length n. So there's 2 to the n strings of length n, but we happen to know that this input is from some subset of them, and so we only need to succeed assuming we're right that the input is from some subset. We don't care what the algorithm is going to do if the input is not from this subset, because we know with certainty that the input is from this subset. So this setting just really happens a lot in practice. Like when you, for example, for Shor's algorithm, you create this implicit database out of the number you want to factor, and then you run effectively a query algorithm on this implicit database. Well, the implicit database, because you're the one generating it, it has a certain property. You know it's basically periodic. And so you don't have to worry about what the algorithm is going to do when the input is not periodic, because you know the input is. So you created this input effectively. So this setting just really happens a lot, and it's also the only setting where you really do get exponential quantum speedups. So when there is a promise on the input, when you restrict when the function is not defined over all Boolean strings but only a subset, then you can have exponential quantum speedups. On the other hand, when the function is defined on every single Boolean string, then no matter how you define the function, there will not be an exponential quantum speedup. Yeah, and it's the intuition is basically because if you have to define the function on every single input, you won't be able to avoid, roughly speaking, you won't be able to avoid having some zero input such that, you know, a lot of kind of adjacent inputs, a lot of neighbors of it are one inputs. So like there are a lot of ways to modify this zero input to get a one input by changing it locally. And so because you're defining the function on every single input, so you must decide for every string whether it's 0 or 1, it turns out for combinatorial reasons, you can't avoid having some kind of zero input that's in a sense close to a lot of one inputs. It's sort of surrounded by one inputs, roughly speaking, just a very rough intuition. And when you have that, so let's say you have zero inputs and it's surrounded by n one inputs, or even just root n one inputs or something like that, then effectively, well, you have to check. If you're computing f, then as a special case of that, you have to check whether the input is this zero input or one of these corruptions of it, one of these neighboring one inputs. And you know, if suppose you could corrupt this zero input just by flipping locally a couple bits, and there's n ways to do this, or even just root n ways to do this, of corrupting this zero input to get a one input, then you're going to have to check all of those root n spots, all of those spots, to see whether they're corrupted or not. But then this is basically like a black box search. This is basically just asking, oh, I have k, like let's say root n different spots that I need to check whether they've been corrupted. You know, even a quantum algorithm requires, well, cannot do better than Grover search, it turns out. So even a quantum algorithm, it turns out, will require n to the 1/4. You know, queries in order to check root n spots. So you know, or in general, if there's k spots to check, the quantum algorithm kind of root n queries. So root k queries to check k spots to see if they've been corrupted. So you know, because of that, then for these combinatorial reasons, if you have to define the function on every single input, you will be stuck with kind of some zero input surrounded by one inputs, or some one input surrounded by zero inputs. And at that spot, the function will be really hard, even for quantum algorithms. Unless you do something trivial like set the entire Boolean hypercube to 0. If everything is 0, then of course you won't have this. But then the deterministic algorithm is fast as well. So, you know, this is sort of the intuitive reason why for total Boolean functions, deterministic and quantum algorithms are polynomially related, and in fact related by power 4. So this is for this combinatorial-like reason. So as you can see, it's not actually a very deep connection. It's not that we managed to simulate a quantum algorithm somehow. No, that's not how the proof worked. It's not that we're simulating quantum algorithm classically. Instead, it's that for the combinatorial reasons, we're forced to have a tough spot in this function, a difficult spot. And the spot is difficult even for quantum algorithms. And the only way to avoid having a difficult spot is to have the function be so trivial that even a deterministic algorithm can solve it quickly. Yeah, so that ends up being the reason why deterministic and randomized and quantum algorithms are all polynomially related for total functions. But as soon as you have a promise, as soon as you don't have to define, you don't have to label every single input as 0 or 1. You can have these, you know, regions, the space where it's undefined in between. Then you don't have to have any inputs surrounded by others, basically. So you don't have to have this situation anymore. And then you suddenly are able to easily define functions with exponential quantum speedup or exponential randomized speedup over deterministic. So you know, suddenly everything is kind of exponentially separated from everything else. Yeah, so you know, that's roughly the intuition you should have for query complexity. Yeah, and Okay, so as I said, I will post some notes for this coming week about some quantum algorithms and how they work in query complexity. Yeah, so for next week, I was wondering if people have a preference between, I can either kind of, we can either do more query complexity, especially talk about how to do quantum lower bounds, for example, or we can first define communication complexity and do kind of a week of an introduction to communication complexity. And then, you know, for the remainder of the course, we can kind of compare query and communication side by side. So, you know, I'm not sure which path I want to go. Again, not for this week. For this week, we're talking about quantum query algorithms, but for next week. So I don't know if people have a preference for how much you want to learn about, like how much this course should be focused on communication. Well, we'll cover some for sure, but do you want this course to be kind of more focused on more like, let's say, half query communication, or more like 2/3, 1/3 for mostly query? I don't know if people have a preference or people don't know what these things are anyway.
So, well, I have a bias because I took the course of query complexity.
Yeah,
I would prefer a little more into communication if possible.
Yeah, I know that's your preference. Yes. So I'll take that into account. Anybody else? Yeah.
Sorry. Okay.
No, it's fine. No, it's good to, yeah, it's good to tell me.
For some, not the same, but a similar reason, I would prefer a little more on, or it would be more new material to have the communication complexity.
Okay.
Even though I'm more interested in query complexity, I recognize there will be more new stuff in the communication one.
Okay. Okay, sounds good. Anyone else?
I think it would be nice to cover communication complexity sooner, just so like then I'll have a better idea of how much I want to focus on each, because at the moment I don't have much knowledge in communication complexity.
Okay. So, all right, let's do that. Actually, any other feedback? Anybody want to disagree? All right, so let's do that. So I guess, you know, not for this week, but for next week, I will post something, basically an introduction to communication complexity. And then if anybody does want to disagree kind of anonymously on Piazza, that's totally fine. So just you can always make an anonymous posts just to remind everyone. Yeah, so I view communication complexity as sort of just a more difficult version of query complexity. That's you know, that's how I view it. So that's also roughly speaking how I will present it, or you know, roughly how I will try to convince you to view it. At least, okay, so there's a lot of things people mean by communication complexity. Some people talk about, well, things like Shannon theory, like quantum Shannon theory, where you talk about the capacity of noisy channels, but in a quantum setting, and things of like entropy measures. Okay, we're not going to focus this course on that. This is I know there's some other courses generally offered, maybe not this term, but Debbie Liang teaches a course that's kind of more focused on this, for example.
That was last term.
So that was last term. Okay. So instead, what we're going to focus on is quantum communication complexity, in that, you know, generally, so the setting is like Alice and Bob are trying to jointly compute a function. They're trying to do some joint computation. Alice has parts of the input, Bob has another part, and they're trying to compute something together. You know, and in this setting sort of has a bunch of simplifications compared to the you know, the more Shannon theory or you know, quantum channel situation, which it's sort of, I guess in a sense I'm saying, because we're willing to lose, for example, constant factors, we're going to not mind losing a factor of 2 here and there, and you know, we're going to assume Alice and Bob can communicate back and forth instead of only one direction. Things like that. It ends up simplifying the situation somewhat, and changing the feel of the study of it kind of feels very different from studying quantum channel capacity, or quantum information, basically. So the quantum information stuff is its own area of study, and it's sometimes also called quantum communication complexity. But I guess I'm warning you that what we will do is a different kind of subfield, also called quantum communication complexity, one that's more analogous, I guess, to classical communication complexity. In which, so as I said, roughly speaking, Alice and Bob are trying to jointly compute something, and then they have quantum internet, so they can communicate over the quantum internet. We'll talk about what that means. So kind of surprisingly, this model, both classically and quantumly, this model where Alice and Bob are trying to jointly compute something, is very closely related to the query model. Although I think it's a bit of a surprising relationship. We'll discuss it. Several of the lower bound techniques that tell you cannot do something in query complexity also have a communication complexity analog. So they also kind of work to tell you cannot do something in communication complexity. But everything is harder in communication complexity. Always the communication analog in every case is more difficult. I kind of view it as, almost, the same but harder compared to query complexity. I think it's good to learn about, if only to gain this intuition. It's not kind of a totally obvious intuition. So I think we will try to, so unless people kind of tell me on Piazza that they strongly disagree, then by default we will try to do some communication complexity next week. So I'll try to post that maybe for next Monday or so. But this week, so by tomorrow, I hope, I will post notes on some quantum query algorithms. I guess many people have seen kind of Grover search, Shor's algorithm, that kind of thing. So, maybe this is not too new, but it sounds like quantum amplitude estimation, at least, people have not seen. So I think the notes will at least roughly introduce the concept, and then I will post the reading papers where people prove or actually give an algorithm for quantum amplitude estimation. So it's a pretty useful algorithmic primitive to know about. It comes up in a lot of other algorithms. Okay, I guess that's the plan. So hopefully I'll post this by tomorrow, and I'll post the reading papers just right after we finish. Anything else? Any other questions? All right. Well, I guess I have one more question I forgot about, actually. What are people's preferences in terms of? So I asked about notes versus video lectures. What are people's preferences in terms of live meetings? So we scheduled here around an hour. Is this the right length? Do you want it shorter, longer? What are people's preferences? Let's see, how do we do this?
So if we have 2 presentations in a week, I think an hour is fine. But if we have to up it to 3, we may want to change it to an hour and a half to allow, let's say.
That's true. Yeah. Although I don't really mean for the presentations to take half an hour each, but you're right, because there'll be discussion afterwards. I mean, I really only want you to talk 10, 15 minutes about a paper, like not make a big deal of it. But yes, you're right. On weeks where we do 3 presentations, we want to make sure we have enough time. But yeah, I mean, I guess I'm partly asking if you want, for example, the live meetings to contain, more technical whiteboard. For example, this time we didn't really do much of a technical whiteboard lesson kind of thing. We could try that. I don't know if people prefer that live or. I mean, of course, the problem is that we would have to try to schedule a long slot, and that's I think a bit more difficult for scheduling reasons, because we don't. people have different schedules. We don't have kind of the registrar setting us a slot where everybody has free time. So yeah, I don't know if that's why I would kind of default to only doing an hour or an hour and a half maybe for the live meeting. But if there's a strong preference to kind of do the lesson live, basically. Okay, how's this? Anybody want like a, let's say, a 2 to 3 hour chunk of live meeting? Maybe raise your hand if you prefer this. All right, I guess nobody is raising hand. Okay, so I'm going to assume that everybody's okay with the current system. Oh, actually, let me ask, does anybody want to switch to a really short live meeting? Okay, looks like also no. Yeah, again, a really short live meeting runs into the problem of not having time for the student presentations. Yeah, okay, so okay, so we will continue with this system. I should mention, yeah, the time of day and maybe even the day of week is not necessarily constant because it depends a little bit on the preferences of the students presenting. So it can't assume, unfortunately, that it will be exactly the same time every week. Yeah, so I'll let you know for next week. It will depend on who wants to volunteer to present the paper. I guess maybe I should. Okay, I guess. I wonder if I should make it 2 presentations. Well, okay, we'll have it. I was going to do only one to start to have people be less scared, but yeah, that will mean we will have to maybe do 3 some weeks later. Okay, yeah, let's go with that. We'll do one to start, start gently, and and then okay, later on maybe we will have to do 3. But again, I don't mean for them to be very long anyway. So I don't think 3 is that big of a deal. I mean, if it's like 10-ish minutes each, and then plus 10 minutes of discussion, we could even fit it in an hour. But we can also allot an hour and a half. Okay. Okay, so if there's no more questions, I guess let's end here. All right, it was great to see everyone. If you have more feedback, definitely leave on Piazza. You can do it anonymously. So if you're too embarrassed to say something, you can say it there. And I hope this live meeting, the recording feature worked, and I will post the recording in that case. All right, so I'll see you next week.